Hello friends. So today we are going to discuss three questions, and the first question, it states that a spring with a spring constant K stands vertically and a mass M is placed on the top of it. The mass is gradually lowered to its equilibrium position. With the spring held at this compressed length, the system is rotated to a horizontal position. The left end of the spring is attached to the wall. The mass is placed on the table with a coefficient of kinetic friction 1/8. The mass is released. So based on this, we have these three questions. Part A, what is the initial compression of the spring? Part B, how much does the maximum stretch or the compression of the spring decreases after each half oscillation? And part C, how many times does the mass oscillate back and forth before coming to rest? So basic figure is given to us. So initially you can say the entire system is vertical, and when this mass is released, obviously the spring is going to compress, and in this compressed motion, or we can say in compressed position, the mass is turned horizontal with the left end is connected to the wall, and then the spring is, you can say, is released, okay, and it is placed on the surface with the coefficient of friction 1/8. Okay, so this is the basic question. So in the first part, it states that what is the initial compression of the string. So initial means when we are having the first case, okay, or we can say this is our initial position of the spring. So we start with part A. And part A, so when the mass is lowered, okay, and it will, you can say, end in equilibrium position when the gravity is going to balance the spring force. Okay. You can say when mass is lowered, it ends in equilibrium when gravity balances the spring force. Balances the spring force. And we have to remember, once the spring is compressed, it is going to apply the force in upward direction, and gravity will be applying the force in the downward direction. Okay. So you can say if this is the compressed position of the spring, and this was our initial position. Now from the initial position, the mass is at compressed state, and we assume that this compression in the spring, or the mass that is being lowered, is by a distance of delta x. Spring constant is of K, so the spring is going to apply a force in upward direction, that is a spring force, and we are going to have a downward direction will be our mg. And spring force we know is equal to K times the compression, that is delta of x. Okay. So we can write this as per the equation. We can say the spring force will be equal to our mg, or we can say that K times delta x will be equal to our mg, and from here we can write that delta of x will be equal to mg upon k. So this is the initial position, or we can say initial compression of the spring. That is our part A. Okay. Now we are going to move this entire system, or we can say we are going to rotate this entire system horizontally. Okay. So basically from here we can write that this compression is frozen. Is frozen when it is rotated horizontally. It means there is no position of this delta of x when the system moves from the vertical to the horizontal. So we can say it is in the frozen condition. Now we come to our part B. And part B asks for the maximum stretch or compression of the spring decrease in each half oscillation. We have to make sure that it is in the each half oscillations. Okay. And for that we are going to use the concept of the energy stored in the spring, okay, and a little bit of the minor adjustment with respect to the friction also. Okay. Or we can say we are going to, okay, let's start with energy first. So we are having our initial energy, and initial energy is, let's suppose, our E of I, and that will be equal to over half k delta x whole square. So this is the initial energy that is stored in the spring, or we can say this energy will be released when the spring our spring is released. Now we come to our energy at the, you can say, the turning point. Energy at next turning point. Okay. So turning point means next maximum position. Okay. And turning point here, we can say that the speed is 0, because we know that maximum position the speed is bound to be 0. Okay. So it means the entire energy stored at this turning point or maximum position is entirely the spring energy. Therefore we can say the energy is purely spring energy, and let us call this as E of F, and we can say this is our half k, and the spring is our delta x prime whole square. Okay, so it is different from delta x, because delta x was only because of the gravity, and when it will be in horizontal, the friction is also going to part play. Okay, so therefore we denote it by this delta x prime. And like I said, there will be also the friction present there, so we can say work done by the friction. Work done by the friction. Okay. And we are going to calculate this work done by the friction. So first of all, we are going to find out what will be the total distance moved by the mass in half oscillation, because specifically for part B it asks for only the half oscillations. Okay. So we can say during half oscillation, the mass moves a total distance and the total distance, we are only interested in the magnitude, we are not going to consider the sign, so that's why we can write this as in terms of delta x plus delta x prime. Okay. And we can also write the equation for the kinetic friction, force because of the kinetic friction. Okay. So we can say that our kinetic friction force, which is our suppose f of f because of friction, that will be equal to mu times mg. Okay. So therefore work done by the friction that is called as wf will be equal to force into our total distance traveled. Force is our mu mg and total distance we have taken as delta of x plus delta x prime. Okay. Now we can use the energy balance equation. So we can say our energy balance equation, we can write that our energy initial is equal to energy final plus energy final and work done because of the friction. So we substitute the equations, we get this as our half k delta square is equal to our half k delta x prime square plus mu mg, and we already know that we are, for the sake of convenience, we are just going to remove the modulus prime. Okay, so we can say that the initial spring energy is equal to final spring energy plus energy lost to the friction, that is the work done by the friction. And we can rearrange it. Okay. And for that we can move towards the left side. So we get this as half k and we have this as delta x square minus delta x prime is equal to, this comes as a mu mg delta x plus delta x prime, and we can just open this term. So we get this half k, we have our a square minus b square, and this will be plus delta x prime is equal to mu mg delta x plus delta x prime, and these two terms are going to cancel out. Therefore we can write that our delta x excuse me, delta x minus delta x prime will be equal to, this comes as 2 mu mg upon k. And so it means from here we can say that the amplitude drops by a constant amount in each half oscillation. Okay, because here everything is constant, mu is constant, m is constant, g is constant, and k is also constant. Okay, so it means in each, you can say, amplitude drops by a constant amount in each half oscillation. So from here we can say that amplitude drops by a constant amount in each half oscillation. And this half oscillation, in terms of amplitude, we can write this as with delta A per half, which is equal to over delta x minus delta x prime is equal to, this is 2 mu mg upon k, and mu we know is our 1 by 8. So we can write this as our 2 upon 8 mg upon k. It means we get this as delta A per half oscillation will be equal to 1 by 4 mg upon k. Okay, so we have to keep this in mind. And so let us try to find out after one half oscillation what will be the amplitude left. So we can say that initial amplitude is already known to us. Initial amplitude, let us call that our x naught, and that was our mg upon k. And after one half oscillation, after one half oscillation, let us call that amplitude is our x of 1, so that will be equal to our x naught minus delta of A. So we can easily solve it. So we get this as our x of 1, and we have our mg upon k minus, and this comes as 1 by 4 mg upon k. So this gives us 3 by 4 mg upon k. Okay. So from here we can clearly draw one important conclusion, that the spring stretch position is going to reduce. We can clearly see that this x1 is reducing because of the friction. So this is quite obvious. And let's try to find out our what happens to the motion when the equation is being satisfied. And for that we know that at turning point we know that velocity is equal to 0. Okay. And the mass will only start moving back if the spring force exceeds the static friction. Okay. So we have to make sure that this condition is being properly satisfied. So we can say the mass moves back if the spring force exceeds static friction. So let us check these conditions. So we know that the maximum friction force, let us call this f of f max, is equal to our mu mg, and spring force at the turning point is, let us suppose, our f of s, and that is our k times x. And motion is going to stop when these two terms are equal. Okay, so we can say that motion stops when our x is equal to, let us call this as our xf. K times xf is equal to mu times mg. Or from here we can say that our xf is equal to mu mg upon k. And so this comes as our 1 by 8 mg upon k. So this relationship is same which I have already drawn here also. Okay. So this is the condition when our this spring force, the motion is going to stop. Okay. Now let's calculate the amplitude after n half oscillations. Amplitude after n half oscillations, and we have already derived that each half oscillation the amplitude reduces by 1 by 4 mg. Okay. You can say that each half oscillation reduces amplitude by, and that is about 1 by 4 mg upon k. Okay. So it means, and we also calculated here that our next is like 3 by 4. Okay, and this cycle is going to be continuous, or x of 2. So this will be our x of 1 minus the reduction in half oscillation. Therefore we can generalize that thing. So we can write that after n half oscillations, we can say that fx of n will be our initial, and n times 1 by 4, and this is our mg upon k. Okay. And we know that our x naught is our mg upon k. So therefore we can write that x of n is equal to mg upon k and minus n upon 4 mg upon k. We can take mg upon k as common. So this comes as 1 minus n upon 4. Okay. And this is nothing but like a, you can say, arithmetic sequence. And we already know that mass stops when our x of n is less than our x of f. So let us substitute it. We get this our mg upon 4, sorry, mg upon k, and 1 minus n upon 4 is less than equal to 1 by 8 mg upon k. And this mg upon k and mg upon k cancels out. Therefore from here we get that value of n is greater than equal to 3.5. Okay, so it means that this will be our the final answer of our part B. Next question. And it states that a block of mass m is supported by a spring on an inclined plane as shown in the figure. The spring constant is k and the plane angle of inclination is theta. The coefficient of friction between the block and the plane is mu. And based on this we have two questions. You move the block down the plane, compressing the spring. What is the maximum compression length of the spring relative to the relaxed length it has when nothing is attached to it? That allows the block to remain at rest when you let it go of it. And it means that if I compress this spring, okay, suppose up till here, and if I release the spring at this position, the spring is this spring is not going to expand. Okay, so basically it is going to remain at rest at this particular position. So this is part A. And part B, it states that assume that the block is at maximum compression you found in the part A. At a given instant, you somehow cause the plane to be frictionless and block springs up along the plane. What must be relation between theta and mu so that block reaches the maximum height when the spring is at its relaxed length? So in part second, this coefficient becomes equal to 0 and obviously it is going to shoot back up the inclined plane. So we have to find out what is the relation between theta and mu, okay, so that it comes at the maximum possible. So it means that let us discuss our part A. And in part A, it states that the spring is compressed, okay, and if we let go this entire system, the spring is not going to expand. So at that particular moment, we can say the block is at rest, or in the simpler terms, it is on the verge of slipping up the inclined plane. So it says that part A, it says that we having a maximum compression and in this maximum compression the block remains at rest. The block remains at rest when released. Okay, so this is our part A. So from here we can write that at instant when block is released, then as per the question we should be having that block should be at rest. The block is at rest. Okay. And from here also we can draw another important conclusion that it is on the verge of slipping. Verge of slipping up the inclined plane. Up the inclined plane. And therefore we can say that the static friction is going to act down the plane. static friction acts down the plane opposing the upward motion. Opposing the, we can say, impending upward motion. Impending upward motion. Now let us write all these statements in terms of our force equations. So we can say forces along the plane so first will be our spring force. And that will be our up the plane. And obviously that is our Fs will be equal to K times X, okay, where X is our the compression length of the spring. Now we come to the component gravity, or we can say component of gravity, that will be down the plane. Component of gravity that will go down the plane, and let us call this as Fg. So you can say f of g will be equal to over mg sine of theta, and we can just draw the figure also. Okay, it's not big complicated one. And the spring is being compressed, something like this. Okay, so this is mass and we have angle theta. So mg will be two components. This will be theta, so we are going to have mg cos of theta, and here we are going to have our mg sine of theta. And the spring force will try to move the up the inclined plane. Therefore, we can also say that the force of friction will be down the inclined plane. Okay. So this is the basic figure, and this is two forces. Third one is our frictional force, maximum static friction, that will be our down the inclined plane. Maximum static friction, and that is our f of f max, which is our mu times n. N is our mg cos of theta. Okay, and this is down the plane. Okay, we have a normal that will be also in this direction, and this is a maximum value of static friction. Okay, so these are the three forces, and that will be acting on it. Okay. And what was asked for? Okay, so we can just, you can say, balance these conditions or equations and get our solution. So we can say we have down the plane, and this is also our down the plane, and we have a spring force up the plane. So we can say our Fs is equal to our Fg plus f of f max, and so this gives us our Kx is equal to our mg sine of theta plus mu mg cos of theta. And from here we can easily find out value of x will be equal to 1 upon k, and this here mg sine of theta plus mu mg cos of theta. Okay, that was asked in the first part. And so we come to our second part. It states that when the friction is suddenly moved. And then we have a part B. And part B said friction is removed. Okay. And so we have our friction is removed. And based on this, we know that the block is initially at rest, which is at x is equal to x max position. Okay. So we can say that our block is at rest, and that position is our x is equal to its maximum position. Okay. So as soon as the friction is removed, the block is having the tendency to move upward direction. Okay. And we are given in question that the block reaches its maximum height. Okay. So which basically means that spring reaches its relaxed length. So in the question we are given that the block reaches its maximum height. Therefore we can say that spring reaches its relaxed length. So based on this, we can draw a important conclusion. So we can say that the final spring compression is equal to 0. Final spring compression is equal to 0, or we can also write that its final velocity is also equal to 0. Now we can usually use the conservation energy law because the friction is not present. Okay. So we can say energy conservation because friction is absent. Okay. So let's find out initial energy, or we can say spring initial potential energy, spring initial energy, and look here USI will be equal to over half k x square, and this is maximum position. Okay. And we can change the, you can say this gravitational part as a reference point. We can assume that when the spring is compressed, the gravitational potential is 0 at this initial point. Okay, that will be more convenient for us to solve. Otherwise it is just, you can say, because the potential energy is just a reference of our you can say height. Okay, if we change our reference point, obviously the potential energy is going to change accordingly. So we can say that at initial point we assume that our gravitational potential is equal to 0, because we have to remember, ideally the spring is compressed completely, but it is not at the 0 level. Okay, so we can treat that this compressed position, the level we change, and this level is having a, you can say, a 0 degree, a 0 our gravitational potential. Okay, because otherwise there will be a combination of height and everything. And now we come to our final energy. And final energy, we know that our spring is relaxed and we are having maximum height. Therefore, we can say that the gravitational potential gain let us call this as UGF, will be equal to our mg, and height will be our x max times sine of theta. Okay. So otherwise it would be a little bit typical to find out the height. So what we did, we calculated or put that the initial point is having gravitational potential is equal to 0. Okay. So that automatically satisfy the, you can say, makes our this calculation easy. So we can directly find out what will be our gravitational potential gain at the height when it is at a maximum height. Okay. Therefore, we can say that now at maximum height we said that its final velocity will be equal to 0. So because of that there will be no kinetic energy, as well as the spring is a relaxed length, so there will be also no spring energy. So in terms of this final energy, we can say that there will be no spring energy because it is in the relaxed state, and obviously there will be also no our kinetic energy. So the only energy that will be possible at the maximum height will be our gravitational potential energy. And initially we were having energy of this USI. So it means USI will be equal to UGF. Okay. This is basically our energy, you can say, conservation. So we can say that our USI is equal to our UGF. So we can substitute this as our half k x square max is equal to, we have this our mg x max and sine of theta. And okay, this is not quite easy to solve. Okay. So we can just remove this x max and we can substitute our maximum part of the equation. X max is our this, because x is equal to our x max. So this is nothing but our x max. So we substitute it, and this will be coming as our half k, and this is our mg upon k, and we have our sine of theta plus mu cos of theta is equal to mg sine of theta. And this k and k cancels out, and our mg and mg also goes away. So we are left with only half sine theta plus mu cos theta is equal to sine theta. And because our half is okay, let us sort it out. We move it to the other direction, and we get this as our sine theta plus mu cos theta is equal to 2 sine theta. So now it is quite easy. So if we get this as mu cos of theta is equal to our sine theta, therefore we get that our tangent of theta is equal to mu. So this is the relationship between the theta as well as our mu. Okay. So yeah, I think these were the two things which were asked. Yeah. Okay. So we come to the third question. And this third question is little bit, you can combination of projectile also. And it states that a frictionless cylindrical pipe with radius r is positioned with its axis parallel to the ground at a height h. What is the minimum initial speed at which a ball must be thrown from the ground level in order to make it over the pipe? Consider two cases. The ball is allowed to touch the pipe and the ball is not allowed to touch the pipe. Okay. So we can just draw an approximate figure. So we are given that we have a pipe. Suppose this is the pipe, and this is the axis of the pipe, and this axis of the pipe is at a height h. Okay. So this is axis of pipe at a height h, and we are given that radius is r of the pipe. And we have said that we are throwing a ball, and okay, so let us assume that from this position we are going to throw a ball with a velocity v, which is making angle theta. So we can divide this v into our v cos of theta, and this will go v sine of theta. Okay. So we have to remember, in the first case the ball is allowed to touch the pipe, okay, and the ball is not allowed to touch the pipe, and with these two conditions we have to find out the minimum initial speed. Okay. So this is the basic question. So let us assume that, okay, So let us consider a coordinate system. We assume that the launch origin is the launch point. X will be our horizontal and Y will be our vertical. So we can say we define our coordinate system so we assume that our launch point is our origin, okay, and the horizontal distance traveled will be our x. So obviously the horizontal axis is our x, and we know that our vertical axis is our y. And we said that it is launched by v naught, not v, and we assume that the projectile is launched with v naught and angle is theta. So we are going to use the projectile equation. These are two standard equations, and let us write them because we are going to use them multiple times. So we are going to use projectile equations. And projectile equations gives us that for our horizontal motion, that is our x of t is our v naught cos of theta times t, and for our vertical motion, we can write this as our y of t is equal to v naught sin theta t minus half gt square. Okay, so these two basic equations we are going to use multiple times. And we also know that at the maximum height of the projectile, the Vy component is equal to 0. So it means at the height of the projectile, you can write that maximum height of projectile we know that the vertical velocity v of y is equal to 0, and therefore we can write that our v of y will be equal to our v naught sine of theta minus gt, that is standard equation of kinematics, and is equal to 0. Therefore from here we can find out that our maximum time will be equal to our v naught sine of theta upon g. And if we substitute this into our vertical motion, we are going to get the maximum value of y. Okay, so we can say our y max will be equal to our v naught sine of theta, and this comes as a v naught sine of theta upon g minus 1/2 g v naught sine theta upon g whole square. So we get that our y max will be equal to, this will be our v square sine square g v naught square sine square g minus and this comes as our half v square sine square upon g, and we get that the maximum value y max is equal to our v naught square sine square theta upon 2g. And now we come to our this you can say the geometry of the pipe, how the pipe is arranged with respect to the given question. So we consider the geometry of the pipe, and partially we have drawn the figure. So we are only interested in the front portion, front cross section rather, and this is the axis part, and let us assume we have a center C, and this is vertical axis and this is a horizontal axis, and center C is given to, its axis is given at a height h, and the radius is of the circle is given as r. So it means this total height is our y is equal to h plus r. And so we can say that if this is our origin, then we can write that our this center of the circular cross section, center of circular cross section, it's which is represented as C, then the coordinate of C we can write this as 0, h. And we can also write the equation. So we can say the equation can be written as our x square plus y minus h whole square is equal to our r square. And like I said, the top of the pipe will be equal to y, which is equal to h plus r. Top of pipe is our y, which is equal to h plus r. And this, you can say, concept or theorem we have studied many times, and it states that for a minimum launch speed, the projectile's highest point must lie directly above the pipe's center. Okay, otherwise, because we have to find out the minimum launch speed. Okay. So we basically means that suppose there is some point here and the projectile is being launched from the various positions. Okay, suppose we launch from it as A, this is B, and directly beyond this is our point C. So if we launch it from point A, it has to travel a horizontal distance as well as the vertical distance. Okay. And if we launch from point B, it is going to travel a horizontal distance that will be less than as compared to A, and the vertical distance will be same for B as well. Whereas if we launch from C, it is only going to travel the horizontal vertical distance. At C, the horizontal distance will be equal to 0. So it means for a minimum launch speed, we can say the projectile highest point must lie above the pipe center. Okay, that is the point where it is going to meet, because if it lie beyond the pipe center, so obviously it is going to lie just beyond the highest point also. So that is vice versa. Okay, so this is our pipe center, and highest point is, let us suppose, our P. So this highest point as well as C are going to coincide with each other. Okay, so we are interested in this highest point. Okay, so it means let's call this C prime, so it is different from C. So it means for minimum speed, our this launch point should be at just beyond the just below our center. Okay. That's why we have taken that this is our origin, and in the start we have also mentioned that the launch point is our origin point. Okay. So it means this automatically we have taken as launch point as origin point. So this thing we have to remember very clearly. Okay. And let me write it here. So we can say that for minimum launch speed, the projectile highest point must lie directly above the pipe center. Above the pipe center. Okay. Because in the part A or part B also rather, it says that this point, the projectile should be able to touch the point B or just past the point P. Okay. So it means the highest point just directly above this center, and that's why we are going to take the origin at as a C prime. Okay. So this is the important part here. Okay. So we have to remember this thing. Okay. We have studied this many times, and sometimes I think some of the teachers also teach them how to drive this particular condition. Okay. And we can also write otherwise the same height would require extra horizontal speed. Extra horizontal speed. Okay. So we have to remember this point. We can, in general, we can just remember it like this. Suppose there are 3 points A, B and C prime. These are the launch points, and from A, B and C prime, the vertical distance it is going to travel will be the same in all the 3, but the horizontal distance is going to vary. A is going to travel the maximum horizontal distance as compared to B, and for C prime is the horizontal distance is also approximately equal to 0. Okay. So this will be position for our minimum launch speed. Okay. And we have to remember this point has to be the highest point of the launch. Okay, projectile's highest point, P. Okay, so this thing is very important, and this is a concept we can just remember as it is. Okay, so it means the apex point, so we can say the apex point, whichever point P, is at coordinate x is equal to 0. Okay, the apex point coordinate is equal to x is equal to 0. Now we come to part A as well as part B. So we have part A, and for part A we have to remember that the projectile is allowed to just touch the point P. Okay, so we have to, this is a part A. We are allowed that ball is allowed to touch the pipe. Okay. So it means if we launch it vertically, this projectile or ball will be touching point P. Okay. So if the ball wants to touch this point P, we have to remember that we have to launch directly below the center point. Okay. And okay, so from here we can draw two important conclusions. First is that the projectile's apex just reaches the top of the pipe. So you can say that projectile's apex, it means projectile highest point just reaches the top of the pipe. Top of the pipe. Top of the pipe is our point P. And second point, this is the concept we are going to use in part B, but I'm going to mention here. So we can say no curvature constraint is needed. Constraint is needed because the projectile motion will be entirely in the straight line in the vertical direction. So there will be no constraint in this curvature. We will discuss that this point in detail in the part B, because there will be our, you can say, constraint of the curvature. And like I said, the projectile apex just reaches the top of the pipe, and we have assumed that the apex point P is our y. Okay, so it means this y will be nothing but our y max. So we can write that our height condition it gives us that y is equal to our y max, which will be equal to h plus r. And y max we already derived, and we can write this as our y max is our v naught square sine square theta upon 2g is equal to h plus r. And we are required to find out the velocity. So let us rewrite the equation that v naught square will be equal to 2g h plus r, and this comes as our sine square theta. So we have to minimize v naught. So only function that is our sine of theta is going to minimize this entire equation. So we are only interested in this. Okay. So we can say that we need minimum v naught. So we can say that our sine of theta should be equal to 1. Or from here we can say our theta is equal to 90 degree. Okay, so it means it will be straight upward projection like we discussed. Okay, so this angle will be 90 degree. Okay. And so based on this theta 90 degree, we can find out the minimum. Okay. So we can say our V minimum can be written as our 2g h plus r and its square root. So this is our minimum velocity for part A. Okay. And let us write this for part A. Okay, because part B is also going to give us almost same equation, but little bit a different way, because there also we require a minimum velocity. So we come to part B, and part B is said the ball must not touch the pipe. Ball must not touch the pipe. Touch the pipe means it should be just able to clear the pipe. Okay. So we can say that ball must just clear the pipe, and for that we can just draw an approximate figure. Once again, we are only interested in this front cross section, and this is our center C, and this we know is this is point P, and this is our height Y. Okay. And obviously it is, if we once again throw from directly below, it is going to touch the point P, which we don't want. We want that the projectile or ball should be just clearing the point P. And let us suppose this point is somewhere here, and if we launch it like this, so it will be just clearing the, okay, let me redraw it again. So it will be just clearing this pipe, something very close to it, but just able to clear it. So it's something like this. And this is our point P. Okay, it's not going to touch the point P, but just moving close to it. Okay. So from here we can also say that the trajectory will be tangent to the circular surface. Therefore we can say that our trajectory is tangent to the circular surface. Okay, so therefore there is a condition will be introduced that will be called as a curvature condition, okay, which we said that there is no curvature constraint in the first case, but in this case there is a constraint or condition, that is our curvature condition. Okay. So you can say that this introduces a curvature condition. So the curvature condition will be introduced. Okay. Now let us, you can say, write the equation, and we know that angle of theta and the angle of the velocity of the projection is our v naught. Okay, that is same. Okay. So let us find out the equation of trajectory near the apex point, that is our P. Okay. So we can say that equation of trajectory near apex and we already know the two I think we have already written the equations. Okay, so yeah, so these are the two equations, equation number 1 and equation number 2. So we can solve these two equations and get a equation of trajectory. Okay, or we can also write it directly, because it is quite obvious to remember the equation of trajectory, because sometimes it is used to solve the question also. Okay, so we can say from equation 1 and 2, from equation 1 and 2, from equation 1 we are going to find out the time and substitute in equation number 2. That is going to give us equation of trajectory. Okay. So we can write equation of trajectory is our y will be equal to x tangent of theta minus jx square, and this is 2 v naught square and cos square theta. So substituting from equation 1 time in equation number 2, we are going to get this equation of trajectory. And we also know that our at apex, we know that our x is equal to 0 and y is equal to y max, which we already know. Okay. Therefore, we can write that we can just draw because this will be approximately a triangle, right angle triangle. So this is our theta and this is our x and this is our you can say y max. Therefore, from here we can say that our x tangent of theta is equal to y max. So in this place we can easily put our y max. So we can write this as, let me write it here, this is our tangent of theta which is perpendicular oblique base. So we get this as y max upon x. Okay. So from here we can say that our y max is equal to x tan of theta. And so we substitute it, we get y is equal to x max minus gx square, and this v naught cos of theta, because we know that our x component is nothing but our v naught cos of theta. So in this place we can write simply our x component, that is twice vx square. Now, like I said, there will be a constraint of our radius of curvature. Okay, so we come back to that, and so we can say radius of curvature of trajectory at apex. And this equation is quite standard. So you can say for curve y of x, we can write that radius of curvature let us suppose that is given as rho. We can denote it any variable, and this rho will be equal to 1 plus first derivative of y, its whole square, and whole raised to power 3 by 2, and divided by double derivative of our y. So this is a standard equation of our radius of curvature. Okay. And so let's find out this y prime and y double prime. So we already know that our y is equal to our y max, so maximum value of y. So it means this y prime will be giving us 0. Okay. And therefore we can say that radius of curvature, if we substitute this y is equal to 0, we get this as y upon y double prime and its magnitude. And from trajectory equation we can find out our y double prime, and that is this equation. I think let us call this equation number 3. So equation 3, so you can say from equation 3, y prime will be equal to, this will be our 0 because it is the maximum value. We get this as minus 2gx upon 2 v naught, sorry, this is our vx square. So 2 and 2 cancels out, and from here we can find out a y double prime will be equal to minus g upon vx square. Okay. So we were able to find out this double prime as well as the single derivative. So we can write, now substitute here, we get our rho is equal to, this will be our Vx square upon g. Okay, we have taken magnitude, so this will be our radius of curvature. Now we know, like we discussed, that the projectile trajectory will be acting like a tangent to this circular pipe. Okay, so we have to remember it is just tangency, no touching. So this is a proximate relationship. Therefore we can say that we are having tangency condition, but the constraint is there is no touching. Okay. So we can just draw an approximate for that. So this was the cross section, and our projectile was like something like this. So it is not going to touch, but it is going to behave like a tangent to the cross section. Okay. Therefore we can, and radius of the pipe is our r. Okay. So we can say that for projectile, to just clear the pipe, so based on this we can derive two conclusions. First will be the curvature of the projectile must match the curvature of the pipe at the top. So we can say that curvature of the trajectory, which we just calculated is our rho, must match the curvature of the pipe. The curvature of pipe at the top, which is our r. Okay. So therefore we can say that our rho is equal to our r, and we are going to substitute here. So let us call this equation number 4. So we can say from equation 4, we get our r is equal to square upon g, or we can say that our Vx square is equal to our g times r. And now we come to the standard relationship which we have already derived, that our maximum y max is equal to h plus r. And y max we have already derived, and so this was our, where it went, this was our y max, so we are going to use it. So we substitute it here, we get this as our v naught square sin square theta upon 2g is equal to h plus r, or we can write it as v naught square, or we can write this as our v naught sin theta whole square is equal to 2g h plus r, and we know that v naught sine of theta is nothing but our this y component. Okay. And okay, So we know that our launch velocity is our v naught, so that will be equal to our x component plus y component. X component is our g of r, so this comes as our g of r, okay. And y component we can find out from here. So this v naught sine of theta is our y component, so this comes at 2g h plus r. So this comes now as plus 2g h plus r. So now it is simple calculation, we are almost done. So we have v naught square is equal to this, we get 2, and you can open it and add it. Okay. So we get this as 2gr plus gr will be equal to 3gr. G we can take as common. So this comes as g will be equal to our 2h plus 3r. So we can say that our minimum velocity will be equal to g 2h plus 3r and its square root, and this is for part B. So this was our important question, okay, and we have to remember that in part A, the important part is that if we want that our launch velocity should be minimum, then the launch coordinate should be just below vertically of the maximum height, okay, which basically means that if it is a maximum height, then the launch should be just below it, so that we get velocity maximum to touch this apex point. Okay, like we said, this point is we touched, the launch should be just below the highest point, okay, because we need this velocity should be minimum. Whereas in the second case, it was asking that this trajectory should be just touching or just going to pass through this. Okay, so in this case, we are going to use the constraint of the curvature, okay, radius of curvature rather. Okay. So these were the two important concepts. So this completes today's 3 questions. Thank you.